Okay, so I am actually trying a new recording today. This is through Camtasia, which I'm going to try to upload to YouTube and see if that works any better than what we were previously using. With any new technology, please be patient. There is a learning curve for me and for you. I want to start by saying I hope you're enjoying your break. I know that you've been inundated with work from all your teachers, and I too have had an exorbitant amount of work. Before you watch this video, you should do one of two things. Either read the chapter or go to the Pages section in our home page and look at the VSEPR videos. They're a little bit long, but they're really good. And VSEPR is something that you get with practice. There's some memorization involved. Wow, that's kind of weird. Okay. There's some memorization involved. The ones that they give you on the AP exam are fairly easy. The ones that you're doing in the lab, in the homework, are like tough case scenarios. So if you have trouble with that, please get a hold of me on Schoology and let me know which ones you're having problems with, and I'll see if I can give you some tips. Before we get started into VSEPR models and shapes today, I want to just review formal charge again. I know I went through it in the last lesson, but it is helpful if you're trying to figure out how to draw a molecule and you're not sure which one is the best shape. Now, here I've given you two examples of HCN, and remember that the preferred geometry is the one that has a formal charge or formal charge is closest to 0. So when we look at the C here, C has 4 valence electrons. That's what we know from the periodic table. So we take what we see, and there are no lone pairs on the C here, and half of what's shared. So we've got 2, 4, 6, 8. 8 that are shared. We take half of that, that's 4. And we subtract that from the valence. So 4 minus 4 is 0. So this is going to have a 0 charge. Nitrogen has 5 valence electrons. It's got 2 here, plus half of shared, so 2, 4, 6, that's 3. So 3 and 2 is 5, minus the original valence, so 5 minus 5 is 0. And hydrogen has 1 minus 1, because that's half of what's shared, so it's going to be 0. So right off the bat, I know that this is going to be the preferred structure because the formal charges on all of the atoms are 0. If we go down to this one, 2, 4, 6, 8, N's got 8, carbon's got 8, hydrogen's got 2. Looks like it could be legit, but when we look at the formal charge, we'll see that the H is going to be 0. Our carbon is going to be the original valence, 4, minus, we've got 2 here, and we're sharing 2, 4, 6. So half of 6 is 3, plus these 2 is 5. So 4 minus 5 gives us a -1. And the nitrogen has 5 valence electrons. We've got 2, 4, plus we've got 2, 4 shared here. Half of 4 is 2, so that's 6. So 5 minus 6 is -1. So here you can see that this is not the preferred structure. Okay? I'm taking the valence electrons that is on the periodic table, and I'm subtracting from that the lone pairs plus half the shared. So let's look at ClO3. We might think that it might have a double bond in it. So maybe we think it's this, or perhaps we think it has one of these oxygens is a double bond. So we can make a double bond. Then these might be 120. They can spread out. And then we've got some valence. Some lone pairs here. And then draw this one ahead of time. Okay, so we have 2, 4. Wait. what do we have here? We have chlorine that's got 7, and we have 3 times, so we've got 7 plus 3 times 6, which is 18. 18 plus 7 is 25, but it's a minus. See the CLO minus, so it's 25 plus 1. So we should have 26 electrons. Let's see. 8 times 3 is 24, and 2 here is 26. We've got 26. And here we've got 2, 4, 6, 8. So we would still have a lone pair. There we go. So 26. Let's see which one of these is preferred. So we've got 6 valence electrons here for oxygen, minus 7, because we have 2, 4, 6 plus half of shared. So that's going to give this a -1. It's going to give this a -1. These are all going to be the same. And our chlorine is going to be 7 valence minus 2, 5, because 2, 4, 6 are shared. Half of 6 is 3 plus 2 is 5. 7 minus 5 would make the chlorine a 2, a positive 2. Let's go down here and see what we have. We know that this is going to be -1. We know this one's going to be -1 because it's the same configuration that we just did. This oxygen is going to change a little. It's going to be 2, 4, and you have 4 shared. Half of 4 is 2. Sorry. So 6 minus 6. That's going to make this one 0. And for the chlorine, we're going to have 7 minus. We've got 2, 4, 6, 8. 8 shared. 8 shared. Half of 8 is 4. Plus 2 is 6. 7 minus 6 is a 1. So this would be 1. So we've got 1, -1, -1. So this actually looks like it's the preferred structure. I have to look that up online. I don't have that one memorized, but according to formal charge, that would be the preferred structure. Alright, that was just a little review of formal charge. We hadn't talked about it in a while. Let's talk about VSEPR models and shapes. What is the VSEPR model and shape? Well, it has to do with molecular geometry. And so the shape tells us the molecular geometry. What is the name of the shape which lends itself to molecular structure? And how is that determined? How is the molecular geometry or the shape of the molecule determined? Well, it's determined through VSEPR, which is valence shell electron pair repulsion theory. It's a mouthful. Valence shell, I'm just going to abbreviate, electron pair repulsion theory or model. I'll put theory/model. It's a way of looking at things to determine how the structure will look three-dimensionally and then two-dimensionally on paper. Now, remember that this only has to do with nonmetals. Okay, so we're only talking about covalently bonded compounds at this point. And this means that valence electrons position themselves to minimize repulsions or repulsion of electron pairs. And why does this happen? Well, basically nature, okay? Bonding and non-bonding pairs spread out. Because as you know, like charges repel. And it really depends on the number of clouds or electron pairs around an atom. And I'll kind of show you what I mean by that. And we're going to go through some pictures in the book. You're never going to be given the pictures that you're going to see of the electron clouds or the shapes and asked to identify them, or nor will you be asked to draw them. You're basically going to be asked to take the knowledge and apply it to a molecular structure and tell me the shape, the molecular geometry, tell me why, tell me the hybridization, which we're going to talk about in this lesson, and the bond angle. So let's look at VSEPR as an example. So you know that each chlorine's got 7 valence electrons, and beryllium has 2 electrons as well that it would like to give up. So basically what happens, this is pretty easy, you've got Be in the middle and you've got Cl on either side. And oh, my electrons got smushed together there, sorry. Those are 2 electrons. So you've got a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons. Now, if we were to look at this, this is basically, you've got the B in the middle, and then you've got your Cl like this, and you're going to see pictures like this in the book, okay? And your Cl like that, as far as the electrons are, the electron clouds. This is obviously a linear arrangement, and it's 180 degrees. And the reason why it's linear is because this is the way that the electrons will be spread out as far as possible. Let's look at another example, BF3. Remember, BF3 is the exception to the rule from the last lesson. It's electron deficient, so it's going to have only 6 electrons, and then you've got your F's coming off here. Notice how I spread them out equidistance. Okay, this you'll see is 120 degrees. And if we were to look, sorry about that, cat just tipped something over. So if we were to look at this from a diagram point of view, you've got something like this. Looks like a daisy that's got its petals plucked off. Whoops. And this angle right in here, or in between each one, is 180 degrees. This geometric shape is called Trigonal Planar, meaning that all of the atoms in the molecule lie in the same plane. There are no lone pairs coming off of it. All right. This didn't print very well in your note packet, but I believe this is in the book. I'm going to explain a little bit. You notice here in the left-hand column, this is hybridization. I'm going to just explain it a little bit. I don't want to go into too much detail because we touch on it, but hybridization is when the electrons that are in the valence shells, when they bond, it's the valence electrons that are bonding. So you might have valence electrons from an s orbital and valence electrons from another atom from a p orbital. And when they bond, they create this hybrid orbital, okay, depending on where the valence electrons are coming from. I'm going to explain later, basically. Well, I'll touch on it now because reinforcement is good. So first of all, let's talk about this number here, the 2's. The 2, the 3, the 4, the 5, the 6, okay? Those are the electron groups that come off the main atom. And what I mean by that is, here, this bond line right here is an electron group. That's a pair. And on this side, you have another electron group. That's another pair. So when you have 2 electron groups, okay, coming off the central atom, that means that it's linear in shape, okay? And the bond angle is usually 180 degrees. They give you some examples here, like CO2, HCN, okay? Now, in this case, CO2 would be nonpolar, but if you look here, this is what it refers to. It says, remember that in molecules where the outside molecules are different, shapes that tend to be nonpolar usually become polar. So here, our central atom is C, and our external atoms are different. So you're going to have polarity here because they're not the same as they are here. Now, just briefly about hybridization. We've blended. We have 2 bond lines, okay? And this is the easy way to remember it. You have 2 bond lines, so this is basically S and P, SP. So this is SP hybridized. All it means is that the valence electrons from the S and P orbitals are what bonded. And this one here, which was like our BF3, okay, you can see that they're equidistant, and that's 120 degrees. And here you have 3 bond lines. Remember, if you only have 1 s orbital, you have 3 p orbitals. So this is s, p1, p2, so sp2 hybridized. So that means that when this molecule is formed, that valence electrons from the s and the p1 and p2 orbitals are bonding. Now, if you have no bonded pairs, it would be trigonal planar, but like water here, okay, H2O is bent. Well, this actually isn't H2O. H2O is usually bent. It's down here. But it's also bent, and it has 2 non-bonded pairs. So it can have the same shape, okay, but different hybridization depending on the number of non-bonded pairs. All right. Tetrahedral, I've got 4 groupings coming off the main atom. The bond lines, bond angles are usually 109 degrees. This is usually a nonpolar molecule. You can see that I've got 4 bond lines, so that's S, P1, P2, P3, so this is sp3 hybridized. Now, the shape changes, okay, depending on the lone pairs. So here I have 1 lone pair. So the electron configuration is still tetrahedral, but the actual molecular geometry of the molecule becomes pyramidal, okay, because it looks like a pyramid. If you were to take off this, it looks like a pyramid. Over here, again, electron arrangement is tetrahedral because I've got 4 groupings of electrons, but the shape is actually bent. Going down here, sorry. Let me put my phone on vibrate. Going down here, we have 5 groupings off the main atom. Okay, so that's going to give us S, P1, P2, P3D, sp3D hybridization. This is called Trigonal Pyramidal. The best way that I can explain this is if you were to take like a little sticky note, okay, and draw a circle. Okay, so I'm going to do this down here. If you had a little sticky note, right, and you drew a circle in the middle, and then you drew 3 bond angles coming off, equidistant, okay? So these three right here are 120. 120, okay? Degree angles. This is your central atom, okay? Now, if you were to take your pencil and stick it up through the bottom and out the top, here's your pencil, okay? Terrible pencil. Anyway, so this would be your fourth atom up here, and then your fifth atom down here, okay? So you've got the three in the middle that are in the same plane, 120 degree angles. Now you've got one coming out the top of the sticky note, out the bottom of the sticky note. They are at 90 degree angles. They are at 90 degree angles from the plane of the paper. Okay, 90 degree angles. This is called trigonal bipyramidal. So trigonal because you have three in the middle, bipyramidal because you've got a top and a bottom of the pyramid, 120 and 90 degrees. And I just explained that the three that are in the plane are 120 degrees, and the fourth and fifth, or the north and south atom, is at 90 degrees to the plane. This can also be called seesaw, okay, if it's got one lone pair, or T-shaped if it has two lone pair, or linear if it has three lone pair. The last one has 6 coming off the central atom, okay, so this is octahedral. So you've got sp3d2, that's the hybridization. It could be square pyramidal if you have one lone pair, or square planar if you've got two lone pair. And it can also, but not usually, be T-shaped or linear. Okay, so that's a little bit about that. Also, I posted a page on Schoology which will help tremendously with the lab and helping you draw some of the models. Alright, so let's talk about some Lewis structures, determining the shape and the polarity. Okay, we're going to do a couple. We're going to do some of the popular ones. We're going to do H2O, CH4, NH3, PCl5, and we're going to do XEF4. Okay, so remember, as we said, we have H2O. We know O is a central atom. You know that you've got an H coming off. Okay? And remember, lone pairs tend to be by each other. So we've got 6 electrons from the oxygen and 2 here, that's 8. So there's 2, 4, there's 6, there's 8. These lone pairs are next to each other, and what you don't see happening is that there's lone pair repulsions going on. These lone pairs are pushing away from each other, which brings these closer together. The shape is bent. And it is polar. So remember, polarity is toward the one that has the higher electronegativity difference. So this gets negative and this gets a positive. And this is the symbol for delta. We can also draw it like this in this direction. The arrowhead points toward the negative side of the molecule, and the plus on the tail is toward the positive sign. Now remember, the electrons though have a tetrahedral arrangement, but the overall molecule is bent. CH4, pretty easy. You've got C, 4 H's coming off. This is nonpolar. The pull is equal and opposite, not to mention that C and H basically have the same electronegativity, so it's nonpolar. And this is going to be tetrahedral. Once you start drawing these and working with them, you'll learn the shapes pretty readily, except for some of the weird ones. NH3, N has 5, and each H has 1. That's a total of 8. So there's 2, 4, 6. so that you know that there's still a lone pair lurking. Has to be on the N. There's my lone pair. Should be 2 dots. Again, there's going to be a dipole moment in the northern direction. Can do it like this, or I can do, whoa, terrible line, like that. This has, again, tetrahedral. All of these so far have tetrahedral electron arrangements, but we're not really interested in that because we have 4 groupings off the central atom. And this is Trigonal Pyramidal. Some people just call it pyramidal in shape. Depends on where you're looking. And just for purposes of language, you have 3 bonding pairs and 1 non-bonding pair, or 1 lone pair. Alright, PCl5. So we have P. The easiest way to do this is, this is an electron abundant. We talked about that. Extra electrons go into the d orbitals, but you can't see that when you're just drawing it. So we're going to do 1, 2, 3, 4. If I had 6, I could very easily put 1 here and 1 here and mimic what I have on this side, but I only have 1 left, so I'm going to put it like that. These are my CLs. So I have 5 pairs. This one is called Trigonal Bipyramidal. Remember, this is the one that's got the 3 in the plane. The 3 CLs in the middle are 120 degrees, and then you've got the pencil coming up through the bottom, and those are 90 degrees to the plane. So this is Trigonal Bipyramidal. And do we have a dipole moment? Usually this is nonpolar. Nonpolar. Why? Because you have the 3 in the plane that are nonpolar because they're 120 apart, and then you've got the north and south. And the last one, XeF4. Xe has 8, and each fluorine has 7. So if you've got fluorine that's got 7, and you've got Xe giving 1 to each of those, so Xe is going to give up 4 of its valence. That means there's still 4 unaccounted for. So that means you're going to have 2 lone pair on the Xe, which is going to squash these together. So you've got electron repulsions this way and this way, top and bottom. So these fluorines get a little bit pushed together due to the lone pair repulsions. This has got 6 groups around it. So the electron arrangement is octahedral, but it's actually considered square planar because when we actually name the geometry, we don't take the lone pairs into consideration. So this is square planar. And square planar is going to be nonpolar as well. Please remember that lone pairs need more space than bonding pairs. So lone pairs are going to smush bonding pairs together. And you'll probably need the chart to guide you when you first do this. Okay, let's move on to hybridization. I've already mentioned it a little bit. All right, the textbook definition of hybridization is basically the mixing of native orbitals to form special orbitals. Now, what should we know about hybrid orbitals? So the hybrid orbitals are basically the special orbitals that are formed. Okay, so these are new orbitals, identical in shape, and they're different from what they were in the free state. I'm just going to put that in parentheses. Different from what they were in the free state. All right, I want to use an example to kind of help drive this point home. Let's look at CH4. So the hydrogens have their valence electrons in the 1s, right? The carbon has their valence electrons in the 2s and the 2p, because we know that carbon ends in 2p2. So you've got, let's see, 1s2, 2s2, 2p2. So these are your valence. Your valence are coming from the 2s and the 2p, and your H is coming from the 1s1. So this is, oops, basically that's what's bonding. So when they bond, you're going to create a new special orbital, or a hybrid orbital, that's different from the 2s or the 2p or the 1s, but it's going to be identical in shape. So for this example, we have S, P1, P2, P3. So this is called SP3 hybridized. Okay. So here it says it has to do with atoms having different orbitals, SPD, F shapes, than basically the molecules themselves. What I want you to keep in mind is that if you have two bonds, basically two bond lines, that's going to be SP. If you have three bond lines, that's going to be SP2. Four bond lines, SP3, which is what we just had. We had four bond lines. Five bond lines is SP3D. Sometimes you'll see it written as D, SP3. You know, I was taught this way. You just keep going in terms of energy levels. But if you see it this way, it's not wrong. And six bond lines is going to be SP3D2, or you might see it written as D2SP3. Don't ask me why they do that. It's kind of weird. If you see, if you have like CO2 and you have a double bond, okay, this double bond counts as 1. This counts as 1 as well. So this is just SP. So double and triple bonds count as 1 when you're doing it. Okay. Let's look at the next page. I'm going to go through a bunch of drawings now, and kind of explain them to you. These drawings are drawings that are in your book, basically. This is just showing you, well, this just went through what I just showed you, the CH4, okay? And it shows you, I'm sorry, up here, this was your S, and then here is your PX, your PY, and your PZ orbitals, and they hybridized, and when they hybridized, they created sp3. Now, these little lobes that you see, these like little things sticking out, they're usually omitted from diagrams in the final diagrams, just to make it more clear. So that's just showing you what it would look like. You would never be asked to draw that or identify that. This is just showing you the energy change, okay? Here you have your 2s, where'd it go? Here's your 2s and your 2p, and when you're done, your hybridized is sp3, it's in the middle. So you have a little bit less energy overall when they hybridize. This is showing you I think I went through this. Yep. This is just, again, showing you an sp2 hybridization, where you know that the p has 3 orbitals, okay? However, you didn't use all of them. You only used 2 out of the 3. So the 2s and the px basically, and the py may be hybridized, okay? And you see the 2p still left here. This would be an example for ethylene. Ethylene is ethene, so it looks like this. And these are your H's. So that's what that would look like. This, I'm just trying to think where we are. Oh, okay. Just trying to stay up with this. In this first diagram here, they're just giving you a 3-dimensional view of the sp2, where you have an s, you have one s and 2 p orbitals that hybridize to form sp2, and 1 p orbital remains unchanged. So this is just another view of the diagram that we saw, and it's perpendicular to the plane of the hybrid. So here, okay, you took one s and you took 2 p's and they hybridized into sp2, and then the third p orbital remained unchanged. In this next diagram, okay, you have, this is showing you well, this actually has a pi bond. We're going to talk about that. We've got sigma bonds and we have pi bonds. And the symbol for sigma is going to be this, and the symbol for pi is going to be like that. A double bond, which is what ethene has, is made up of a sigma bond and a pi bond. Sigma bonds, the electron pair that is shared in the same plane, okay? So the electrons that are being shared here are being shared in the same plane as the atoms. As you'll see in the next picture, that's the sigma. The pi bond, okay, which is the other half of the double bond, is shared in a plane either above or below the central atom plane. So, am I going to test you on exactly what a sigma bond is? No, but you should know what it is. This was the symbol, okay? So the electron pair is shared in an area centered on a line running between the atoms. And as we said, a pi bond the electron pair occupies, or the electron pair being shared occupies the space above or below, basically the sigma bond. Okay, what is extremely important that you know is that a single bond is made up of only sigma bonds. A double bond is made up of a sigma and a pi bond, and a triple bond is made up of a sigma and two pi's, or sigma pi pi. Okay? So in this case, the triple bond, you'd have your sigma in the middle here, in this area, and then you'd have one pi bond above and one pi bond below. In the double, you know, the electrons basically choose where it is that they're going, either above or below. All right, moving on. A few more diagrams here. In this picture, this is basically showing you the orbitals used to form the bonds in ethylene. So they're showing you all the sp2s where they're all hybridized, okay? And then, so the greens, okay, well, these were your S's, the purple ones, and then your greens are now the sp2 hybridized, and the blue are the PZs, basically, that weren't being used. In the next diagram, they're showing you simply sp. This is where one s and one p orbital are hybridized. So here is one s, and here's your px, and they're hybridized to form an sp, and an sp hybridization is 180 degrees, as you can see right here. This is just showing you the s and p hybridization here, okay? And the other ones, the sp2s. This is all three, for the three orbitals. This is showing you the energy diagram, okay? So you have an S and one P, so here's your SP, and then you have unused P's, because remember, you have two S's, S1 and S2. In this diagram, you have the orbitals of an sp hybridized carbon atom. So this is showing you carbon with your sp hybridization, and this is showing you in the bottom one the orbital arrangement for an sp2 hybridized oxygen atom. Okay, they're showing you for oxygen and they're showing you for carbon. Now remember, this makes sense because oxygen ends in, oxygen is 6, so it's 1s2, 2s2, 8 total, 2p4, right? 5, 6, 7, 8. There you go, 8. So here are your 3 sp2 orbitals and then your one that wasn't used. Where in this one you have 1s2. I'm just showing you the difference. 2s2, 2p2. So you have this. Okay, so here's your sp, your 2 yellow ones that were hybridized. Okay, and then the rest that aren't. Because remember, your p's hold 6 electrons. Okay, we didn't use this one, we didn't use this one, and we didn't use these 2. So those are your 4 blue ones. The 2 that were used were these 2 right here. Same thing down here. We didn't use this one, and we didn't use this one. That's why we have our 2 blue ones. Just want to make sure I can make it as clear as possible for you. And this is just showing you it put together. The orbitals used to form the bonds in carbon dioxide. Note that the carbon-oxygen double bonds consist of 1 sigma and 1 pi bond, the Lewis structure for carbon dioxide, basically. So here you can see you're hybridized. Here's your sigma bond right here. I'm in the plane. Okay, sigma bond, and then a pi bond. So your pi bond, they're not showing you definitively because you don't know if, let me change colors, you don't know if it's going to be here or here, and then on this side here or here. It's a double bond. It's either going to be above or below the sigma bond. Now we're getting into very complicated. Again, you will never have to draw or discern these, in any way. But I want you to be able to understand what's going on. I've got 1, 2, 3, 4, 5 groups of electrons coming off the main atom. So that's going to be dsp3. And this is for phosphorus, as you can see in the middle. Please note that the set of 5 dsp3 orbitals has a trigonal bipyramidal arrangement. Okay, this is where I showed you 1, 2, 3. These angles are 120. And then you've got your pencil basically coming up through the middle like this, top and bottom. Okay, this one's still here. I'm going to kind of overshadow it. I'll move it over a little. This angle right here is your 90-degree angle. That's with your north and south atom that it makes with the plane. And this other one over here is D2sp3. I've got 6 coming off, okay? And this should make sense. This is octahedral. So basically, you've got 4 in the plane. 1, 2, 3, 4 in the plane, and then you have 1 coming up through the bottom, your north and your south. And these should be all 90 degrees. These should be 90, 90, 90, 90 here, and then this should be 90 here. This is just showing a little bit more about, this is straight out of the book. It's showing you the different basic shapes. We've been through these: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now that's given that all the electron pairs are bonded. We get into some different structures when they're not bonded. Okay, we have some different names for things. All right, let me see if there's anything left that I need to talk about. Just looking through my notes. Okay, the only thing left are some AP problems, and we're going to do those on the first day back to class as a group together so that I can answer any questions that you have and I can see how you're thinking about these different things. All right, that's it. If you have any questions, get a hold of me through Schoology. I will talk to you later.